Welcome to the Ask AI channel. Please click the subscribe button so you get all the new episodes. Why is it taking so long to solve the problem of entanglement? Quantum entanglement is a complex and fascinating phenomenon in physics. It's often described as an invisible link between distant quantum objects that allows one to instantly affect the other. However, this description can be misleading. In reality, entanglement is better understood as information. The challenge in solving the problem of entanglement lies in several factors. 1. Conceptual understanding. Quantum entanglement is a departure from classical lines of thought. It challenges our everyday notion of reality as a collection of things in the world with physical properties waiting to be revealed through measurement. This makes it difficult to intuitively understand and hence, to solve. 2. Experimental constraints. The processes used to create entangled photons in a real laboratory are constrained by many experimental variables. These include the shape of laser beams used in experiments and the sizes of small crystals where the entangled photons are created. 3. Technical challenges. Work is ongoing on issues such as the stability of qubits, error correction techniques, and the design of large-scale quantum circuits. More qubits and more advanced control techniques are needed to achieve the ability to solve large-scale problems where quantum computers can excel compared to existing classical computers. Despite these challenges, scientists are making progress in understanding and harnessing quantum entanglement. It's central to quantum computing, quantum networking, and the fabric of space and time. So, while it may take time, the journey to unravel the mysteries of quantum entanglement is well underway. If some unknown force is faster than the speed of light, does that trigger theories not currently viable that could link time, space, and quantum mechanics? The discovery of a force that travels faster than the speed of light could indeed have significant implications for our understanding of the universe and could potentially open up new areas of theoretical exploration. However, it's important to note that according to our current understanding of physics, particularly Einstein's theory of relativity, nothing can travel faster than the speed of light in a vacuum. If such a force were discovered, it could challenge the fundamental principles of physics and necessitate a re-evaluation of theories that link time, space, and quantum mechanics. For instance, quantum theory and relativity theory both require a new concept of space-time. The velocity of light not being infinite calls for a redefinition of spacetime on large and cosmological scales, while the quantization of action in terms of a finite, non-vanishing, universal constant requires a redefinition on very small scales. Moreover, the notion of time as one common continuous time variable and nature evolving continuously in time has to be replaced by an infinite manifold of transition rates for discontinuous quantum transitions. If a force could travel faster than light, it might necessitate a further redefinition of these concepts. However, it's also important to remember that any new theory or discovery would need to be rigorously tested and confirmed through experimental evidence before it could be accepted by the scientific community. Until such a force is discovered and its properties thoroughly studied, it remains a hypothetical scenario. How big is a wavelength? Could it be very large, spreading across the universe? The size of a wavelength can vary greatly depending on the type of wave. For instance, the wavelength of a 100 MHz electromagnetic, radio, wave is about 3 meters. The wavelength of visible light ranges from deep red, roughly 700 nanometers, to violet, roughly 400 nanometers. For sound waves in air, the speed of sound is 343 meters per second, at room temperature and atmospheric pressure. The wavelengths of sound frequencies audible to the human ear, 20 Hz - 20 kHz, are thus between approximately 17 m and 17 mm, respectively. In theory, a wavelength could be very large, even spreading across the universe. The electromagnetic spectrum spans frequencies ranging from below 1 Hz to above 10 to the power of 25 Hz, corresponding to wavelengths from thousands of kilometers down to a fraction of the size of an atomic nucleus. There is no known limit for long and short wavelengths. However, such large wavelengths would correspond to very low energy waves, and detecting or utilizing such waves could present significant challenges. It's also important to note that all these measurements and theories are based on our current understanding of physics, and future discoveries could potentially change our understanding. If matter is never lost, then data is continually moving from one state to another. Yes, you're correct. The principle of conservation of matter, also known as the law of conservation of mass, states that matter cannot be created or destroyed in an isolated system. This principle is a fundamental concept in physics and chemistry. In the context of data, it's a bit different. Data can be transformed, processed, and moved, but it doesn't behave the same way as physical matter. When we delete data, it seems to be lost, but what's really happening is that the storage space that the data was occupying is now available for new data. The original data may still exist until it's overwritten by new data. So, in a sense, you could say that data is continually moving from one state to another. However, it's important to note that while data can be transformed and moved, it can also be duplicated, which is not something that can happen with physical matter under normal conditions. This is one of the key differences between data and physical matter. Theoretically, if a wavelength spread across the universe, then we could observe or change data at one point and know instantaneously the result galaxies away, that is faster than the speed of light. Theoretically, if a wave could span the universe, it might seem like we could use it to transmit information instantaneously across vast distances. However, according to our current understanding of physics, this isn't possible. The speed at which changes in a wave state propagate is limited by the speed of light, according to the theory of relativity. This means that if you were to change the state of a wave here on Earth, the effects of that change wouldn't be felt at a distant point in the universe instantaneously, but would instead propagate at the speed of light. This is a common misconception related to the concept of quantum entanglement, which is often described as spooky action at a distance. While it's true that entangled particles can affect each other's states instantaneously over any distance, this doesn't allow for faster-than-light communication. This is because the state of the entangled particles is random until measured, and once measured, the state can't be changed. So while the measurement results are correlated in a way that requires faster-than-light interaction, no usable information can be transmitted in this way. So, while it's a fascinating concept, our current understanding of physics doesn't allow for faster-than-light communication or observation, even with a wave that spans the universe. Can you explain quantum entanglement in more detail? Quantum entanglement is a phenomenon that occurs when a group of particles are generated, interact, or share spatial proximity in such a way that the quantum state of each particle of the group cannot be described independently of the state of the others. This includes when the particles are separated by a large distance. Entanglement is a primary feature of quantum mechanics not present in classical mechanics. Measurements of physical properties such as position, momentum, spin, and polarization performed on entangled particles can, in some cases, be found to be perfectly correlated. For example, if a pair of entangled particles is generated such that their total spin is known to be zero, and one particle is found to have clockwise spin on a first axis, then the spin of the other particle, measured on the same axis, is found to be anticlockwise. However, this behavior gives rise to seemingly paradoxical effects. Any measurement of a particle's properties results in an apparent and irreversible wave function collapse of that particle and changes the original quantum state. With entangled particles, such measurements affect the entangled system as a whole. Such phenomena were the subject of a 1935 paper by Albert Einstein, Boris Podolsky, and Nathan Rosen, and several papers by Erwin Schrödinger shortly thereafter, describing what came to be known as the EPR paradox. Einstein and others considered such behavior impossible, as it violated the local realism view of causality, Einstein referring to it as spooky action at a distance, and argued that the accepted formulation of quantum mechanics must therefore be incomplete. Later, however, the counterintuitive predictions of quantum mechanics were verified in tests where polarization or spin of entangled particles were measured at separate locations, statistically violating Bell's inequality. In earlier tests, it could not be ruled out that the result at one point could have been subtly transmitted to the remote point, affecting the outcome at the second location. However, so-called loophole-free Bell tests have since been performed where the locations were sufficiently separated that communications at the speed of light would have taken longer, in one case, 10,000 times longer, than the interval between the measurements. According to some interpretations of quantum mechanics, the effect of one measurement occurs instantly. However, it's important to note that while entanglement allows for correlations that can't be explained by classical physics, it doesn't allow for faster-than-light communication, because the outcome of measurements on entangled particles is random and can't be controlled. Therefore, no information can be transmitted through entanglement alone. Are you saying because the particles are random, information can't be transmitted simply because you can't measure them? Yes, that's correct. The randomness of the outcomes of measurements on entangled particles is a key aspect of quantum entanglement. When you measure an entangled particle, the outcome is entirely random and cannot be controlled. This means that you can't use entangled particles to transmit specific information, because you can't determine what the outcome of a measurement will be until you actually perform the measurement. Furthermore, once you've measured the state of an entangled particle, the entanglement is broken, and the particles are no longer correlated. So even though the measurement results of entangled particles are correlated in a way that requires faster-than-light interaction, no usable information can be transmitted in this way. It's also worth noting that while the measurement of one particle of an entangled pair does affect the state of the other particle instantaneously, this doesn't violate the principle that information can't travel faster than the speed of light, because no actual information is being transmitted between the particles. The measurement results are random and independent of the experimenter's choice of what measurements to perform. Therefore, the experimenter cannot use the measurement of one particle to instantaneously control the state of the other particle. If I was writing a book of science fiction, how would I explain a human changing module state and traveling on universe-wide wavelength faster than the speed of light? In a science fiction context, you could introduce a concept where humans have developed a technology to manipulate their molecular state into a form of quantum entanglement. Here's a possible explanation. In your universe, scientists have discovered a new particle, let's call it a quantum resonance particle, QRP. This particle has the unique property of being able to exist in a state of quantum entanglement with other QRPs, regardless of the distance separating them. Humans have developed a technology, perhaps a quantum resonance chamber, that can infuse a person's molecules with these QRPs. When a person enters the chamber, their molecules are carefully and precisely manipulated at the quantum level, replacing certain key particles with QRPs. This process is known as quantum resonance infusion. Once the infusion process is complete, the person's molecular state is now entangled with the corresponding QRP field, which exists in a state of quantum superposition across the universe. The person can then manipulate their own quantum state to match that of any location within the QRP field. This is done using a device known as a quantum state modulator. When the quantum state modulator is activated, it causes the person's quantum state to collapse, effectively choosing a new location within the QRP field. Because of the properties of quantum entanglement, this change in state happens instantaneously, allowing the person to effectively travel to the new location faster than the speed of light. Thank you for your time. Please hit that subscribe button and enjoy more compelling stories from the Centered Canuck. See you next time.